Hi, welcome to this video about surface tension and capillary action with a special focus on water. My name is Karl-Erik Hagentoft. I work at the Chalmers University of Technology in Sweden. On the right hand side here you see a picture of a soap bubble, and we will investigate what kind of pressure we have inside a bubble of that type. And we also have a picture of capillary rise in a small glass tube, how water is rising up in the water. In a tube like that, and we will investigate that as well. With this picture we see a small steel wire, a loop of a steel wire actually resting on the water surface. And we know of course that steel is more dense and should normally sink to the bottom. But somehow here the wire is supported by a surface membrane. And this is a phenomenon of surface tension. To explain surface tension, we can look at the pictures down to the left, where these blue circles are symbolizing water molecules, and the arrows are symbolizing the bonds, the hydrobonds between the water molecules. So deep inside the liquid, there are bonds in all directions that are kind of a net force between the molecules. But at the surface, it's a bit different. And there would be a net force downwards and towards each other. This cohesion between water molecules actually keeping the molecules in the top surface there tight to each other. They're holding each other and form this type of membrane. We can symbolize that or try to explain it with a membrane of a lot of springs in between the molecules. And of course, depending on how you are stretching this membrane or pushing it together, this will be associated with an energy, a surface energy. We have a surface tension, the gamma has the unit joule per square meter. So we have actually the surface energy equal to the area times this surface tension coefficient. And a soap film like this one, we have two sides. So the surface energy for this soap film is 2 times A times gamma. And we will make a mind experiment to understand a bit more about the forces involved. So we have a fixed frame here. We have a soap membrane, a soap film in between the frame and the moving wire. And we start to moving the wire. And this is associated with a certain force, F. And if we look at the energy balance of that, we look at how much work we are performing if we move the wire delta x. And it would be force times the movement delta x. And this should be in an energy balance with the change in the surface energy, which is delta A times gamma. In this case 2L times delta x, since we have surfaces on the both sides. And we change the order a bit in this equation here. We can find that gamma is equal to the force divided by 2L with the unit of Newton per meter. So gamma means, or surface tension means, is force per unit length of the surface edge. And this is a way of interpret the surface tension phenomena that would be very handy. Gamma is a constant for water at 20 degrees. When water is close to air, is 0.0725 Newton per meter. Now we're looking at a soap bubble. To the left we have a bubble here with the radius r, and it will form a sphere in order to minimize the area and thus the surface energy. And in this mind experiment, we are pulling apart the hemispheres and extend in the middle of the bubble with a stretched out delta x. This also means that we will enlarge the surface area with delta A, which will be equal to the circumference times delta x times 2, since we have two surfaces here. Assume that we have a pressure in the bubble, and the pressure is different from what we have on the outside. And we need that pressure difference to understand how big is this force F. And the pressure difference will be acting on the whole surface area here, but we will show that it will be important is the cross-section area pi r square. We'll look at that now in another experiment, mind experiment. So if we look at a shape of a bubble like this, it's not really a bubble, but a shape like this, and we have a different pressure in the inside and the outside. The black arrows resembles the forces due to the pressure difference, and we have force due to the pressure difference times the area, local area. And the sum of all those forces to the right must be equal to the force to the left, otherwise this will start moving in one or other direction, which they of course do not do. And we get a simple formula for F, which is equal to the pressure difference, P plus, times the cross-section area, pi r square. So then we have shown how we can come up with that formula. Now we are looking at the surface energy and the work performed and put them equal. And the change in surface energy is equal to delta A times gamma, and we have already formulas for that. And the force, we have formula for that as well, times delta X. And putting these together, we find actually the pressure inside the bubble. And it's 4 gamma divided by R. And we can do the same exercise with the water drop, but then we just have one surface. So this will be half the amount, it will be 2 gamma divided by R. This latter formula also working for an air bubble in water. This picture shows capillary rise in tubes. This is a well-known phenomenon. We see in the smaller tube, the glass tube that is down into water, we have a high rise of water, but in the tubes with a bigger radius that are not so thin, we have less capillary rise. And we'll try to find out these capillary rise, how it's working. The capillary forces, or the capillary action, is due to attraction between the water molecules and the walls of the glass. We talked about the cohesion before, between the water molecules, the attraction between water molecules, but we also have an attraction between the water molecules and the silicon, for instance, in the glass. And this is actually stronger than the bonds between the water molecules. So we have a net attraction that actually moves up the water molecules along the wall. And a meniscus is formed, and this attraction between the wall that is strong also keep or holding up the meniscus up and lift up the water meniscus a bit up to corresponding to this capillary rise. And this should balance the weight of the water underneath. If we look at the meniscus, it's at least in small tubes. This is spherically shaped to minimize the surface energy. And we know that the force that holds up the meniscus is due to surface tension is equal to the circumference times gamma. We also have a contact angle, and this is something you have to measure. That's something you have to find out by experiments. This contact angle is equal to 0 for water meeting glass, but it's different with other fluids and other solids. For instance, mercury in glass is 140 degrees. That means this meniscus is flipped with the top upwards, and it's actually pressing down the mercury if we have mercury in glass, so the capillary rise is negative. So let's look at what this will cause. We have this surface tension, and if we look at the vertical component of that, Fc, that is actually what should be able to balance the weight of the water underneath the meniscus. And Fc is equal to circumference times gamma times cosine theta, so we get the vertical component. And for the gravity forces, we have the mass of the water times g, and we use the volume, pi r square times h, times the density, we get the mass, and voila, we have the equation for the capillary rise, which is equal to 2 gamma times cosinus theta divided by r, rho, and g. And this is what we can expect, that r is in the denominator. So if we have a small r, we have a high capillary rise. That was expected, and we know from experience. We can also derive the formula using what we know about bubbles from the previous slides. So if we have a tube like this to the right, and we have certain contact angle, and we can assume that the meniscus is shaped as a sphere, we can find the radius of this sphere, capital R, from using a bit of trigonometry. And then we know the pressure inside a thought bubble there, equal to 2 gamma divided by R. But since we don't have really a bubble here, we have a contact with the outer air, or the air, which has the atmospheric pressure. We have to interpret this P plus as a negative pressure underneath the meniscus instead, so we can maintain this pressure difference across the meniscus. So we have a capillary suction instead, so a suction force to look at. If we use this way of describing the problem, we still have the balance due to gravity and the mass of water, and this force of suction would be equal to the suction pressure and times the square, cross-section area, pi r square. And we arrive, of course, with the same formula. But understanding this way of looking at this phenomenon as a suction could be quite fruitful. This picture shows microscopy pictures of aerated concrete or lightweight concrete. The one on the top right is with the biggest magnification. And what we see is a lot of gaps, a lot of holes, a lot of pores. If we compare these gaps with the radius of the tubes we looked at before, we have a resemblance, of course, and we can expect some type of suction of water rise in materials that are porous like this. And here is a sponge dipped into water, and we know that this will suck up water, of course, into these small pores. They're very small, and it's very great forces involved here, very, very, very high suction. Here's a picture of an experiment I did with sand from the beach, and put the sand pillar here into water, colored water. You can see it rises up roughly 1 decimeter here. If we look at clay, which has very, very fine grain sizes, just a fraction of a millimeter, we can expect same type of pores and distance between the grains. So there will be very, very high suction, and we see that the capillary rise is up to 10 meters. In fine sands, it's up to 3 meters, and the sand of this type I've shown here on to the left, we get a rise of a few decimeters. And if it's a coarser sand, it gets less, higher up. In building technology, when we want to, for instance, protect a foundation from sucking the foundation to suck up water from the ground, we can use gravel, which is even more coarse, big or small pebbles or small stones. And then that way we avoid water sucked up into the construction. We also have the phenomena when two materials are in contact with each other. So if we have two materials and one has much finer pores, we have a higher degree of higher suction. Actually, the materials with the finer pore can suck water from the one with coarse or greater pores. Here are some microscopy pictures again with materials that are not necessarily porous, but they have cracks, and we see how very fast the water can be sucked up, assuming that we have water in the bottom, sucked up into the material through the cracks, like tiny tubes. There's a lot of resistance in the tubes because it's a very narrow path, but the suction will sooner or later suck up water deep into the material. And we have other building related issues. The left hand side here shows the end of the wall cladding, and after rain and the water has driving rain has hit the facade and it's flowing down the cladding and ends up in the end wood of the cladding. And if it's sucked up and it's not protected properly, you can see on the right hand side how the wood will decay and rot. And the upper right picture shows building construction, and it's a timber frame construction, and it's just rained, and the building hasn't been protected, the building site hasn't been protected from rain, and we see a huge amount of, a lot of water can be sucked into the wood. And also if the wood is not separated from the concrete, then the wood can also suck moisture from the concrete directly. So some conclusions or summary. We have looked at the surface tension energy and found out that that is equal to the area times the gamma. And the gamma is the surface tension. It can be interpreted as a force per unit length. Newton per meter is the unit. We have seen that there is overpressure in a bubble with two surfaces, and we're also seeing that there is an overpressure in a drop or bubble in fluid. We have looked at the contact angle and found out that this is something we have to find experimentally, and it's important for the capillary forces. We have established formulas for the capillary rise and also the interpretation of capillary suction. And that was all. Thank you very much.